Hey everybody, welcome to episode 4 of the Blueprints to C++ programming series. Today we're doing something differently. Today is exercise time. Before I go into more theory and new topics, I thought about applying everything that we've learned so far in the last episodes to a small exercise. So let's have a look at the outline. One thing that I want to show beforehand is I created a GitHub repository where I place files, slides, and everything for you to access, especially now for this episode, for the exercise, the graphs, and the results, and all that stuff. In this exercise, we are going to convert a graph which is fictitious and has no meaning, so it doesn't really run and stuff, but it just will show you several aspects of converting and stuff that you might have seen in the past in your work, in other people's work with blueprints, that is really common and often used when it comes to programming in blueprints. After analyzing that graph, we are going over some tips and tricks or how to convert several nodes. I will show you exactly how to figure out which functions to call and so on. And then it's really exercise time. Then it's you to apply this on your own time, trying to figure out, create that class and the functions. And if you've done that, then it's time to come back and we are going through the final results. So before we dive right in, let me show you the GitHub repository. And like I mentioned, from now on, all slides of this episode, future episodes, and even the previous episodes are now available on the new repository. And I will also put coding results and other files if need be in the future and stuff. So you can find the GitHub under the following link, and I will add this to the description of the episode. But let's have a look first at the repository. So here it is, and in the future I will have more playlists and stuff, so we will have more folders. Right now we have the Blueprints to C++ folder. If we click here, you can see from episode 0 to episode 4 we have all these folders, and if you click inside you can see like the slides from that episode that you can download and have a look at. And for today's episode 4 there are some more files in there, so if you're following along and are really doing the exercise, then what you need is either the image here. So this is the graph that you can then start converting from if you don't want to really recreate it in blueprints, because this graph doesn't really work. It's just showing a fictitious example. So here you can download either an image file or you can download the UAsset file that you can place in your blueprints folder. But once you do this, you get some errors because some cone classes or the cone actor class is not found and so on, but it doesn't run. So if you really want to have a look at in Unreal itself, you can have a look at the graph in that UAsset file or on the image file. The test actor H and test actor CPP are the final results. So if you're really serious about exercising, and I really stress that you really do and really do the exercise, that you can then have a look later at the outcome or the final result, but not look at it beforehand or something. So, but it's up to you. So anyways, let's continue with the graph itself. Let's have a look at the graph. It's a bigger graph with several math nodes. Let me scroll in a little bit. So the main thing that we are going to convert and create functions from is this setup cone actor and setting the actor location. And you can see here a lot of math calculations, round, floor, clamp, and so on. But before we go deeper into that graph, I want to mention something that I kind of missed in the last episode where we covered U functions. Someone in the comments asked me about if it's possible to combine specifiers. And of course, it is possible. Not every combination is viable though. You will get compiler errors. But there's one thing that is really possible and important if you want to call blueprint implementable events, for example, from blueprints. Like what we did last time is we defined a blueprint implementable event, and this is perfectly fine. We can convert it as a custom event in blueprints, and we can call it from C++. But it was not possible to call it from blueprints. And so if you add the specifier blueprint callable to the blueprint implementable event, then you will be able to call the implementable event from blueprints as well. And this is why I did this setup. So we have begin play. In this case here, we are doing some delay, and then we are calling the setup cone actor. The setup cone actor for the conversion will be a blueprint implementable event. And I want you to add the specifier or even test out, then in the exercise, leave the blueprint callable or don't add the blueprint callable to it, to the definition, and then add the blueprint callable to the implementable event definition. And then you will see that once calling this gives you a compiler error, and once you add the blueprint callable, then it works perfectly. The reason why I do these delays is to show you in some ways how real-world blueprint crafts work in some ways, where somebody is doing some initializing work, then is waiting for a couple of milliseconds or seconds before they call another function. And so sometimes you don't have the luxury of really converting a C++ class from the start, or where you need to have blueprint code as well. And that's what I mentioned in the beginnings of the first episodes, where I told you that it's not C++ only and not blueprint only, but it's a good combination of it. And in this case, what we would leave alone is this call here. So we would call the test func from the cone actor, have the delay, but then we create a blueprint callable function that has all this code in it that does all the calculations. And I can show you the result of the graph. So if you look at this, how big this graph is, or how complicated these calculations are not complicated, but they are really huge in mass. So if you compare it to the result here, and this is what we are striving for, and this is what I want you to do in the exercise, is create a blueprint implementable event that can be called from blueprints that has these functions here, and then create a blueprint callable function set cone actor location that has all that logic inside. So this will be the exercise. But before we go into the exercise, let's analyze the graph a little bit more, and then I will show you some tips and tricks on how to convert these nodes. So as you maybe remember in the first episodes, when I told you that every kind of node here is like a function call into C++. And so if you're now trying to figure out or approaching how to convert these nodes into C++, into one single C++ function, then what you can see is, okay, you have some groups, we have like 4 vectors that we need to create. And each vector is calculated by this whole, let's say the second vector is these calculations, the first one is this one, and so on. So you can structure your code based on how you create these vectors, and at the end add them together and set the actor location. But how do you find out, okay, how to get round or floor, or even these special functions like get the right vector and so on? How to find the equivalent C++ functions. So what Unreal often does, or what is part of their game framework, are these blueprint function libraries that they created that, like in this case, for example, Round uses the Kismet math library. This is a blueprint function library. You will be able also to create your own libraries, and this will be part of future episode to show you how to do this. But what we are covering today is the Kismet math library, and there are several others like Kismet array library when we later see array operations and so on. So every little node, the multiplier, the plus, the modulo, is all part of the Kismet math library. And in a few seconds I will show you how to access this. But there's also one other thing that I want to stress or show you, is that, like I mentioned last time, each green node, this is a pure function. Each time you call it, it's recalculated. You can see it like here. We get the cone actor, get actor location, create from the x value the floor, add +1, and from the same value create the modulo from it. And what you might think is, okay, we have calculated this whole thing for once and then we have the same value, but this value here, this is when we add the plus, then it's calculated once. Once we hit this node, it's calculated again, the whole graph here. The same goes with the get right and get forward vector. The whole stuff here is calculated for this node and for this node. And so in C++, you can really use local variables to calculate, for example, this delta once, save it in a local variable, and then you don't have to do it again. The same with the floor value, for example. Then you see, like what I often see in Blueprint code is where you have some of your own variables, like we have here, width and height. We multiply it, then we add the speed and so on. Then you see again down here, you have width and height, it's multiplied, but the result is used differently. And down here, you can see it again. So every time this is called, this is calculated. It's not really big of a deal from a, let's say, these calculations really don't take time, but you have function calls down to C++ from these libraries. And it's much cleaner if you in C++ do it once, it's more readable, and it's better to just calculate this once, have a const local variable that you can then use to add the speed or create the round from or the floor or whatever. So this is just what I wanted to show you, that usually in those blueprint graphs, there are calculations that are done several times that you maybe not really thought about, or that it's not that obvious once you see a graph like this, but it's really important, and for performance and for readability, if we convert this to C++, that we can then get rid of these multiple calculations, make the code cleaner, and so on. So before we get into the exercise, some more tips on how to figure out which functions to call. Okay, before we go into the exercise time, like I mentioned, I want to show you some tips on how to find which function to call in C++. On every node, when you hover over it, you see like target is, and then something like in this case here, target is Kismet math library. If you look at here, target is actor. In this case, actor is the cone actor. And this is a way how to figure out where this function comes from and where to call it. Like if we want to get the actor location, we say cone actor.get actor location. Sometimes though, the names that you see in blueprints are not the names that are in C++. Most of the time they are, but sometimes they probably from old UE3 and more times they have different namings, but using the display name meta tag, they change the name to another name. Like for example, the clamp float, you won't find this function name like this for the float value. So this is what you have to figure out. But before we go too much into theory, let's have a look at code. Okay, in the editor, let's just use the cone actor. I just want to show you some examples. So the Kismet math library that the most functions are called from. But how do we find the Kismet math library? From the Unreal naming conventions, you may find out that these blueprint libraries have the U in front of the class name. So Kismet Kismet math library is the name of the blueprint function library. In Writer, the include file will automatically be added if you're using like the IntelliSense to access the math library and so on. In Visual Studio, even with the Visual Assist plugin, there you need to figure out how to, or figure out which include file you need to use. So what I did before I used Writer, I kind of like found the name and then Googled it, and it automatically found the online documentation, and in there you find the include path which to use. And once you do it for a long time, then you really know these path names by heart, like some actor components, like static mesh component and so on. They are under components slash and then that name and so on for most Kismet stuff, like the Kismet math library. And if you can see, if we type uKismet, you can see there is the math library, you have the array library, you have string libraries, and many, many more. And these are usually found under Kismet. So if we look at three nodes that I want to have a look at with you, that's delta, clamp, and lerp. These three, because there are three different ways or three different possibilities for you to use it. Let's look at clamp first. So if we look at clamp, there is a clamp function, but it's for integers. It's not the float version. If you want to find out the function name, let's say if we use clamp and hit F12, you can see the implementation of that function. If we go to the header file, you can see this function is called clamp and it has the display name clamp integer, but that's not what we're looking for. We are looking for, so what we are looking for is the clamp float, this function here. This is what you can see, clamp float. That's the real function that we are needing. And what you can see here, it's called fclamp or float clamp. And so you really see this is how you find out the real function names to call. And if you're going in there now into the implementation, and that's the one thing that I want to show you, that one possibility is this is just a wrapper around the standard, the new fmath library in the C++ game framework. So if you're calling clamp float from blueprints, it will call this function. And this function will call again the fmath function. So when you're doing the conversion, what I want you to get away from this is not to use the Kismet math library fclamp, so that we would call like fclamp and add the values in here and use this, but rather use the fmath and do the clamp. And it's a template style function that can take in the integer and floats and so on. So this is one possibility. So if you're looking at these functions, really analyze these and see, do I really need to call the uKismet math library function, which you can do, or really, if we are going into the implementation, really use the fmath version from that. And you can see here down here, finterp2 uses the fmath. Here, max, there are so many functions in here that use the fmath. So be aware of that. And the second possibility is to actually use the Kismet math library call itself. In contrast to the clamp function, for example, which uses the fmath library, this function only uses or calculates values based on the input parameters. So it's perfectly fine to use, in this case, the uKismet math library lerp. And in our case, just as a hint, the lerp, this lerp that you've seen here is not our lerp because it's lerp vector and we have lerp floats. So I know that it's called vlerp for vector lerp. If you look at it, it's similar, calculating vectors, adding, subtracting, multiplying them. So it's perfectly fine to use this lerp function if you're converting that node later down the road using the uKismet math library function. And then there's also a third possibility, which in our case is the delta rotator. The delta rotator is found in the CPP file of the Kismet math library, and it's the third possibility because you can either call this function, use this just as a function call from the uKismet math library, or you can rather say, okay, you look at what it's doing, it's subtracting two vectors, two rotators, and then normalizing them. So what you can actually do is, what I would do, like I said, this is my personal thing, but you have these two possibilities. So what I would do, if, let's delete this, if we have a rotator, rot1 and rot2, and if we just say rot1 minus rot2 and then normalize the delta. So this is instead of that function call here. So you could either do this or use the uKismet math library as, if you look at for delta, you see the normalized delta rotator, and then you would say rot1, rot2 and call it. But the reason I do this is because this is just a function call which has two lines and is not inlined, that if you maybe do this several times and stuff, it's a lot easier for me to say, okay, I see what it's doing, it just calculate stuff in 2 lines and get the result back and call a function on that. I think, in my opinion, I don't want to call that function, but you can do it as you like. So this is the third possibility, using either the function call itself or look at it, what it's doing, and then decide copy this out of it or use that function. I've shown you these ways on how to figure these functions out that you can call. And one thing that I wanted to show you, if we have the Ukismet math library and you see nodes like for example, this one here, converts integer to a float. And these are usually function calls that start with conf, for example, and then you can see here into float. And if we go into that function to see what it does, it's just casting that into float. Because in blueprints, there's not the possibility to do stuff like that. So you have the base C++ functionality that need to be called from blueprints. And this is how they created all their functions. But when you convert this in C++, you mostly don't even need to do this. So this is just also stuff that I wanted to show. And this is what I figured out over all those months when I converted that blueprint template project that I bought and where I learned the most from. So this is how you can really figure things out. So as a recap, look at the target. Target is Kismet math library, or target is actor, or you can see here delay is Kismet system library. But there is possibility, by the way, to do a delay. We use timers for that, but this is a more advanced feature that I will cover in future episodes. So what I want you to do now, and I think it's now time for the exercise, to really figure things out, how to convert this, try your hands, create a function to place your code in, and from what you learned from previous episodes and so on, and try to figure out how to convert it. And once you've done that, I'm taking a break here, and then you can come back, continue where we left off here, and I will show you the result of how to do it. Okay, welcome back. I hope you had a fun time converting that graph to C++. And now to show you how I've done it, let's have a look at the end graph. So here, like you've seen in the beginning, we have the begin play, which calls that blueprint implementable event. This has stayed the same, and it calls the set cone actor location. So let's get into the meat of things and first have a look at the header file. Here I defined these 3 properties that were part of the original blueprint: the width, the height, then the cone actor. And as I mentioned in previous episodes, it's best to forward declare classes so that you don't import that header file in here in the header file of that class, but rather in the CPP file. All of them are added anywhere in blueprint read write. Then I defined the setup cone actor as blueprint implementable event and blueprint callable. So here we combine these 2 specifiers, and then we have the set cone actor location defined as a blueprint callable. So let's look at the function itself. So first I check that the cone actor is not null, because when I access it here, then I need to make sure that it's a valid pointer. Then, like we've seen in the examples let's go to that graph, where we calculate the width times height several times, have the get actor location several times from cone and from the test actor. So this is where I calculate them first, get the actor location, get the actor location from cone actor, and calculate width time height. And then we have seen that we have 4 vectors. So for the first vector, I think the calculation stuff is easy. The only thing that you probably had to figure out was the absolute node. So as you might have guessed, that Ukismet math library call just calls the fmath absolute function. So we use it here. And for the second vector, the 2 functions to figure out were round and floor. And these are called from the math library as well, called round to int and floor to int. And the modulo is basically just the operator in C++, so there's nothing new. Vectors just multiplied with standard operators like multipliers, additions, subtractions, and so forth. So this is how it works here. Then for the third vector, what was specific, it had a make vector and used these calculations. So we just in C++, we just define the vector and then set each XYZ value based on that. And what we had in the tips section with the clamp, here you can see I used fmath clamp for that. And then the rotator, for the fourth vector, I calculated the cone actor.getActor rotation minus the actor rotation and then normalized it. So I didn't use the normalized delta rotation function. And then we have three specific things that are also a little bit not complicated, but you had to figure out were the right vector, the forward vector, and the lerp. The lerp I told you was to use the vlerp from the Kismet math library itself. And the others were like function calls in the Kismet math library that basically for the forward vector, it just calls delta.vector, that function call. And for the right vector, it just uses this one line. So I decided to just use this and not call the Kismet math library for it. And then at the end, I calculate the vector by adding it all together and then calling cone actor.setActor location. And that's it. That's our first example. So on the GitHub, you can find the test actor H and CPP files, like I mentioned. And so that's it for today. I hope you liked that first exercise. I think I will do several in the future, just as we get deeper into more advanced topics and other things, that we can create more complex graphs and functions, and so that you will be able to see and convert those graphs, how to do it best, how you can convert it. And so this was just a small introduction of exercises that will come in the future as well. So I hope you had fun with this one. The next video, or the next 3 videos, will be about the T-array, the T-set, and the T-map, the Unreal Collection classes, and these will be short ones, but these are really important topics that need to be covered. So look forward to them, and I'll see you next video. Bye bye.